Hello everyone and welcome back to my channel. In my first lecture, I discussed with you guys what is nucleophilic substitution by molecular reaction, why it is called SN2 reaction, what is Walden inversion and so forth. So today we are going to discuss different important characteristics of this reaction. In addition, I'm also going to show you few simple and quick tricks to solve SN2 based problems. So keep watching this video. So if you remember, in my previous lecture, I mentioned that SN2 reaction leads to inversion of configuration. But why it happens? So to explain that, I'm going to use the same reaction where methyl bromide reacts with hydroxide ion and give you methanol as a product. So to show the inversion of configuration, I have oriented these three hydrogens in the reactant on the left hand side, and in the product they are oriented on the right hand side. So the first explanation for inversion of configuration is that the hydroxide ion, it will never attack from the direction where CBr bond is situated. It will always attack from the opposite side of the CBr bond. Always from the opposite side of the CBr bond. So now the second explanation that why it is attacking from the opposite side of the CBr bond is that the sigma star antibonding orbital, which takes these two electrons from nucleophile, it is also situated on the opposite side of the CBr bond. And therefore, you will notice that in the product, the carbon-oxygen bond that has been newly formed is always opposite to the CBr. So now you know what is the reason. I'm going to repeat one more times. OH negative, which is a nucleophile, never attacks from the side where CBr bond is situated. It always attacks from the back side of the CBr bond. And the reason for that is that the empty sigma star antibonding orbital, which takes these electrons, is also situated on the opposite side of the CBr bond. So I'm sure by now you know what is the reason for inversion of configuration in SN2 reaction. So the second important characteristic of SN2 reaction is effect of bulky groups on reactivity of alkyl halides towards SN2 reaction. So to understand this, I have shown you 4 different alkyl halides along with their reactivity order, where A is the most reactive towards SN2 reaction, followed by B, then C, and finally D. So to understand this, let's compare the reactivity of A with the D, where A has got 3 hydrogens. On the other hand, D has got 3 methyl groups. Alright. So in case of A, where you have very small size of 3 hydrogens, you can see that the approach of the nucleophiles on the carbon is very easy because the size is very small of the hydrogens. On the other hand, if you look at these 3 methyl groups, the approach of nucleophile on the carbon is going to be difficult, and this effect is called steric hindrance. So you can say that the steric hindrance caused by these 3 methyl groups in case of tertiary butyl bromide is more as compared to these 3 hydrogens in case of methyl bromide. So the second reason is the electrophilicity of the carbon. Now you know that nucleophile attacks on the carbon, right? And why it attacks on the carbon? Because this carbon has got delta positive charge and bromide has got delta negative charge. So in case of tertiary butyl bromide, these 3 methyl groups, they are increasing the electron density on the carbon. In other words, they are making this carbon less electrophilic. And that is the second reason why nucleophilic attack is not as comfortable or as convenient as in case of methyl bromide. So if you have understood these concepts, you can easily explain the reactivity order of B and C, where B is more reactive than C. So again, apply this knowledge. In case of B, you have 1 methyl. On the other hand, in case of C, you got 2 methyl groups. So obviously, steric hindrance caused by C is more, and that is why it is less reactive than B. I hope you find this video useful. Feel free to ask should you have any queries, and please don't forget to like, share and subscribe my channel for further updates. Thank you.